Today, we're diving deep inside the battery cell to look at the absolutely critical quality control gauntlet it has to run during assembly. And believe me, these aren't just your standard run-of-the-mill checks. These are the make-or-break steps that guarantee the safety and performance of the batteries that, let's face it, power pretty much everything now. So, let's get into it.
And that quote right there really says it all, doesn't it? It just perfectly sets the stage for what we're talking about today. The stakes are incredibly high. We're not just worried about a cell that maybe doesn't hold a charge as well as it should. No, we are talking about preventing absolute disasters. A single, microscopic flaw slipped in during assembly can unravel the whole thing, and that is precisely why this process is so intense.
So here's our game plan for this explainer. We're going to follow the journey of a battery cell as it's built. First, we'll touch on why that internal structure is so important. Then we'll get into the nitty-gritty, checking its first connections, making sure it's sealed up tight, literally looking inside it without opening it up, and then putting it through the ultimate electrical safety test before that final voltage check.
All right, let's kick things off with the absolute foundation of it all, what I like to call the invisible architecture of power that's tucked away inside every single cell.
The core challenge here really boils down to two huge things. First, you have to make sure that this incredibly delicate and complex internal structure, that tightly wound jelly roll or those perfectly stacked electrodes, is physically flawless. And second, you have to guarantee that the positive and negative parts stay electrically separate. If you fail on either of those fronts, you're not just looking at poor performance. You are creating a direct highway to an internal short circuit, which, as we all know, is the root cause of the most serious battery safety incidents.
So that brings us to our very first physical quality check, the weld. This is truly the first point where power can actually get in or out of the cell.
So what exactly is the weld in this context? Well, think of it as the bridge connecting the internal superhighways, those thin copper and aluminum foils, to the outside world via the terminals. The quality of this one tiny spot has a massive impact on the cell's internal resistance and its ability to deliver power. A bad weld is basically like a bottleneck on that highway. It creates resistance, generates heat where you don't want it, and just chokes the flow of current.
Now, what's really fascinating here is how manufacturers attack this problem from multiple angles. It's a full-on assault to ensure quality. First, automated systems use things like optical or ultrasonic sensors for a really fast, non-destructive check of the weld's shape and size. Then, super precise instruments measure the electrical resistance right across that weld. Any little spike in resistance flags a weak connection and a potential hotspot down the road. And finally, some cells are sacrificed for the greater good in a destructive pull test, where they literally measure how much force it takes to rip the weld apart. It's all about making sure it's both electrically and mechanically sound. All right, so the internal connections are solid. The next huge step is to make sure all that energy and all that delicate chemistry is safely contained. And that brings us to testing the hermetic seal. A hermetic seal is exactly what it sounds like. It's got to be perfectly, absolutely airtight. Its job is simple but critical. Keep the inside in and the outside out. It has to prevent moisture, which is public enemy number one for lithium-ion chemistry, from getting in, while at the same time stopping the volatile electrolyte from ever getting out. So you might be wondering, how in the world do you test for a leak that might be completely microscopic? Well, one of the most sensitive methods involves putting the cell in a vacuum chamber and using a trace gas like helium. If even a few atoms of helium sneak out, a detector will scream bloody murder. Another really clever trick is pressure decay. They just slightly pressurize the cell and watch it. If that pressure drops, even a tiny bit over time, you've got a leak. Okay, so the cell is welded and it's sealed. Now for the really tricky part. How do you inspect what's going on inside without, tearing the whole thing apart? I mean, this is the million-dollar question for non-destructive testing, right? The anode, the cathode, the separator, they're all stacked with a level of precision that is just mind-boggling. So how do you confirm that everything is still perfectly aligned after the cell's been sealed up and handled?
And this is where some seriously cool technology comes into play. You've basically got two leading methods for the job. On one side, you have X-ray and CT scanning. It's just like in a hospital. They create these detailed 2D or 3D images that let engineers see right inside the cell. They're amazing for checking critical dimensions, like making sure the anode to cathode overhang is perfect, and for spotting big physical problems, like a stray metal particle. Then, on the other side, you have acoustic imaging, which uses high-frequency sound. And this is great at finding things X-rays might miss, like areas where layers are pulling apart, what we call delamination, or tiny gas bubbles trapped inside because the electrolyte didn't fully soak in everywhere.
Okay, Now we're arriving at what is arguably the single most important safety check in the entire assembly line. This is it. This is the final, ultimate safety gate before a cell is cleared for activation.
It's called high potential testing, or HiPOT for short, and the concept is both simple and incredibly powerful. You hit the cell with a voltage far, far higher than it will ever see in real life, and you see if the insulation can take it. The entire test is focused on the integrity of one component, that super thin separator membrane that keeps the anode and cathode from touching.
Now, here's the crucial thing to understand. The HiPOT test isn't looking for a major dead short. It's designed to find something much more sneaky, what we call a latent soft short. Think of it as a tiny, hidden threat, a microscopic tear in the separator maybe, or a tiny conductive particle that's almost bridging the gap. It's the kind of defect that might not cause a problem right away, but it's a ticking time bomb that could lead to a catastrophic failure months or even years down the line.
The process itself is, well, it's brutally efficient, and there's no gray area. High voltage gets applied, the system watches for any current trying to leak across. Even a tiny, minuscule amount of current means there's a flaw in the insulation somewhere. There's no passing grade, no acceptable range. Any leak at all means the cell has failed. It is immediately rejected, no second chances, no questions asked.
So, after surviving that incredibly intense electrical stress test, and once a cell has been filled with electrolyte and steeled for good, it is time for one final confirmation. This is the last checkpoint in the assembly process.
The open circuit voltage, or OCV check, is like a fundamental health screening for the cell. After it's filled with electrolyte and has had some time to rest and stabilize, technicians simply measure the voltage across the terminals with no load on it. It's the battery's natural resting potential, and it tells you an awful lot about what's going on inside. A healthy OCV reading is a simple but really powerful confirmation. It tells you, number 1, that the electrolyte is doing its job. Number 2, that the anode and cathode have successfully set up their chemical potential. And number 3, that the cell has reached the state of charge that you'd expect after its very first formation cycle. It's basically the final thumbs up, signaling that a healthy, stable electrochemical system has just been born.
So think about it. Every single cell goes through this incredible, intense series of checks, verifying welds, seals, internal alignment, and insulation before it ever gets a chance to leave the factory. Which really leads to a final thought. With this amazing level of scrutiny already in place, what does the future hold? What is the next frontier in battery quality assurance that's going to push safety and performance even further? That's a huge question for the entire industry to be thinking about.